Alrighty, a room temperature oxygen molecule has a typical kinetic energy of about 6.21 times 10 to the negative 21 joules. If it has a mass of 5.31 times 10 to the negative 26 kilograms, how fast is it moving? Well, we know kinetic energy is 1/2 mass velocity squared. So let's do a little algebra and solve for velocity because that's what we're looking for. So velocity is going to be equal to 2 times kinetic energy divided by mass, square root the whole ball of wax. So we're going to take a look at this. 2 times the kinetic energy, 6.21 times 10 to the negative 21 joules, divided by the mass of our oxygen molecule, 5.31 times 10 to the negative 26 kilograms, square root the entire ball of wax, and let's see what we get. 2 times 6.21 times 10 to the negative 21 divided by 5.31 times 10 to the negative 26, square root all of that, and I get a velocity of 484 meters per second. And you might say, wowza, that's really fast, and it is. Molecules are going very, very fast. It's a good thing they're very small, and there's a lot of space between them. All right, number 6. How much work is required to stop an electron that is moving with a speed of 1.9 times 10 to the 6th meters per second? When we're talking about work is required to stop it, so the work to stop it is going to be equal to the kinetic energy that it has. We have to put in as much work as the little electron has in order to make it stop. So we're actually have to determine the kinetic energy that the electron has. Well, kinetic energy, as you are aware, is equal to 1/2 mass velocity squared. We are told the velocity of the electron. We are going to have to look up the mass of the electron. That you can look up on that orange sheet or that constant sheet. The mass of the electron is given there. So the energy possessed by that electron is going to be 1/2 the mass of an electron. Electrons are very, very small things. The mass of an electron is 9.11 times 10 to the negative 31 kilograms, very tiny. The velocity in this case is 1.9 times 10 to the 6th meters per second. Square that velocity, and let's see what we end up with. 1.9 times 10 to the 6th quantity squared times 9.1 times 10 to the negative 31 divided by 2, and I ended up with a kinetic energy of 1.64 times 10 to the negative 18 joules. That is the kinetic energy of that electron. One electron, not a lot of kinetic energy. Lots of electrons, lots of kinetic energy. Number 7, a baseball with a mass of 140 grams is traveling at 32 meters per second when it strikes a fielder's glove. It moves a distance of 25 centimeters backwards while being caught. What was the average force that the glove exerted on the ball? Here's the way this works. The kinetic energy that the ball possessed is transformed into the work that is done on the ball in order to stop it. So the kinetic energy of the ball is 1/2 the mass of the ball, the velocity of the ball squared, and the work done on it is going to be the force applied to the ball times the distance over which that force is exerted. We are told the distance over which the force is exerted, that 25 centimeters. We know the velocity of the ball. We know the mass of the ball, and we're asked to find the force. So let's solve for force. So force is going to be equal to 1/2 mass velocity squared, and this whole thing divided by displacement. So 1/2 mass of the ball is 140 grams. We're going to convert that to kilograms, 0.140 kilograms. Velocity of the ball, 32 meters per second. That velocity is squared, so square that velocity. Displacement, it moves 25 centimeters backwards. We have to move that decimal 2 places to make it meters, MKS system, 25 meters. And let's put those numbers into the calculator. So I'm going to have 0.5 for my 25 times 0.14 times 32, quantity squared. And I think I did that wrong. 32 squared times 0.14 times 1/2 divided by 0.25, and I end up with 287. Now, what units should be on it? It should be newtons. Let's double check we actually get newtons. I have up here a kilogram. Meters squared per second squared. So meters squared over seconds squared divided by meters. Let's see what happens here. This meter will cancel one of those. I end up with a kilogram meter per second squared. A kilogram meter per second squared is 1 Newton. So the units there worked out very, very nicely. Let's do one more. Number 8. At an accident scene on a level road, investigators measure a car's skid marks to be 88 meters long. The accident occurred on a rainy day with the coefficient of kinetic friction was estimated to be 0.42. What was the speed of the car when the driver slammed on the brakes? All right, this is the logic. When the car was traveling down the road, it had a certain quantity of kinetic energy. That kinetic energy was transformed into, when the driver put on the brakes and began to slide, then the work that was kinetic energy was transformed into work done against friction. Okay, work done against friction. So the kinetic energy is 1/2 the mass, the velocity squared, is going to be equal to work done against friction. Well, you know work is force applied times distance. This is on a level road, so we don't have to worry about components or things at angles or anything like that. Work done against friction means this is the friction force. Well, friction force, you are aware, is mu times normal force. So let's take this equation and take it one step further. 1/2 mass velocity squared. Friction force is going to be mu normal force times the distance over which that friction force was worked against. If we have a car sitting on level road, force of gravity down will be equal to normal force up. And what that means is normal force will be equal to force of gravity. So I can replace normal force with force of gravity, which is mass times acceleration of gravity. So one more time, 1/2 mass velocity squared equals mu mass acceleration of gravity times displacement. Now, the mass of the car does not matter. It doesn't matter if it's a semi-truck or a Kia. Those fall out. We want to know what was the speed of the car ahead of time, so this is what I'm looking for is V. We know mu, we know gravity, and we measured the skid marks. So we can solve for V. So let's make this pretty, and let's solve for V. So 1/2 V squared is going to be mu, acceleration of gravity, times x. Let's do some magical algebra and solve for V. V then is going to be mu, acceleration of gravity, times x. We're going to multiply both sides by 2 to get rid of the half, so this is going to be multiplied by 2. How do you undo a square? You square root it, and I am now going to put some numbers in here. And so the velocity is going to be the square root of 2 times the coefficient of friction. The coefficient of friction on this day is 0.420. The acceleration of gravity is our old friend, 9.8 meters per second squared. The skid marks were measured to be 88 meters, so that's the distance. So 2 mu AX, put this in my calculator, 88 times 9.8 times 0.42 times 2, square root the whole ball of wax. The original velocity of the car was 26.9 meters per second. Let's double check those units. Meters times meters is meters squared divided by seconds squared, and all of this was under the square root sign. Square root of meters squared per second squared is meters per second. That is good. All right, we will see you